Okay, then we can maybe if there are no further questions, then we can maybe continue with the next speaker, which is Estela Reynoso Masset from the Norwegian University of Life Sciences. And she will be speaking about understanding the long-term fate of naturally occurring radionuclides at a non-remediated legacy site containing acid-forming elements. Gail. And the floor is yours. Thank
you. Yeah. Okay. We go like this. There's a lot of things on the screen here, but hi, my name is Stella. Thank you for the introduction. And today I'm presenting part of what is kind of a summary from Mila's PhD project. No. First, just briefly, what is alum shale? And it's a black shale, a form of black shale that contains silicates, organic matter, and sulfite and carbonate phases, and is generally enriched in elements of environmental concern, but also of natural occurring radionuclides. In the Scandinavian alum shale formation is known for having high levels of uranium. And these rocks are generally acid-generating rocks, especially this in this area at the south of Norway, in the Oslo field, it's called. And when these rocks are exposed to water and air, the sulfide minerals in these rocks are oxidized, and they produce acid rock drainage. So the mining, when there is mining, road construction, and building construction, there is a large production of rock waste, and this can be a problem because this waste, if is weather, then it produces ARD, and then there is a dissolution of minerals and a release of contaminants. And in Norway, this alum shale rock waste is considered special waste when it's acid generating, and currently the Norwegian industry is searching for better solutions for handling this waste, and this is also part of another project that we have in the faculty. And but the message is that we still have a gap in knowledge on weathering processes of the alum shale and its environmental impact. But that was in the current days, but in the past there was not so much awareness of this problem. And an example is that in the 80s and 90s, there was 50 tons of alum shale from the Oslo, that it was extracted from Oslo, in the Oslo city when constructing buildings and tunnels, and it was disposed on a private land that is called Taraldrud, which is a bit south of Oslo. And it's been in the news recently. It's ongoing in the news, and the most recent this was that we don't see here. That is in October 2022, and this Nature Conservation Association, they are claiming that it's one of the Norway's most dangerous waste landfills, and that heavy metals and radioactive uranium seep into a stream. And the water flows into the drinking water for almost 50,000 people, including the university. NMBU is part of the 50,000 people. And so what is Taraldrud? Just a brief description. So this is alum shale rock waste that was disposed in this area, and it was built at the E6 highway that is running from Sweden to Oslo. It was built on top of this alum shale, and it's been monitoring, and then in 2006 they found acidic runoff. So then they built, and that it was reaching this little stream. And there is, so they built this, can we see it? Yeah, they built this precipitation pond as a mitigation action, and also they've been liming the area to increase the pH of the woods. But for us, it's only 15 minutes drive to campus, so it was a perfect place for Mila to have a study site, and it's been part of her thesis, and that she's going to submit this year. And we submitted a late paper at the end of May, the first paper. And it's looking at the environmental impact of this alum shale legacy site. In Taraldrud, we collected, so this is surface map, and this is in red shows the location of the waste rock deposits, and we had this is the precipitation pond, and we collected water, also water measurements, soil sediments, and we got alum shale from these locations that from NGI when they did an exploration, checking and monitoring. And we have a reference site which is north from this area that it doesn't is not affected by this alum shale, acidic rock drainage. So on the first paper, the span video. So paper 1, we look at the environmental impact and process and geochemical processes. And we measure a lot of elements, so we have a lot of other elements, but here is only focused on the radionuclides. And from the alum shale characterization, we've seen that it contains a high uranium, and that this uranium is highly leachable. And we saw that the radium and lead is less leachable, so it's not leached from the rock. And the thorium was in between; it was higher than the radium and the lead. So we have a remobilization of these natural occurring radionuclides from this source rock waste. And then this in the waters, the radium was below limit of detection in all of the surface waters, and the thorium and uranium were highly enriched in the precipitation pond water. And this was actually in the form of low molecular mass species, so they are mobile species, and also a bit on the mixing zone area, which I forgot to explain, which is the connection between the pond and the stream. And these radionuclides are highly retained in the soils and the sediments. We had a high enrichment of uranium in all of the soils and the sediments from the pond and this mixing zone area. And we had also quite a lot of thorium. And its top is basically on the top layer, so 15 centimeters, in the first 15 centimeters. We want to highlight that most of these soils are about the Norwegian limit for low-level radioactive waste, and that's all of the concern of trying to remediate this site. And also to highlight that there's, because of the sulfide dissolution, there is also high concentrations of iron and sulfate and sulfur in these soils. So as a quick summary of what's happening, or we think that is happening in this site, is like there's an ongoing weathering of the alum shale that is producing acid rock drainage. Then is mobilizing uranium and thorium, and because of the pH of the pond, where we cannot see there, that has been 3 for the last 3 years, is the water in the pond is 2.9. These species are immobile species and complexed with sulfate because it is high concentration of sulfate. But when they are moved with the water flow, they are retained in this mixing zone area before the stream. And we are suggesting that is because of there is a high because of it's been absorbed to iron and manganese oxyhydroxides, and also potentially with organic matter, because these soils contain high organic matter. And so it's not reaching the stream. So as per now, there is like very low concentrations of these radionuclides in the stream. And I think that's the reason also the DSA, the Norwegian authority, are not going to remediate. For now, this is staying as it is now. So the pond is doing the job. But for us, it was quite interesting to try to understand why is this uranium retained, is remobilized, and why is it retained in these soils. And so we did a study on the solid phase speciation to understand what is happening in these soils here. This is the mixing zone area. So we collected the cores from these 3. So this is the outlet of the pond that it goes into the stream. And then we have 2 sediments. And we had bin time twice, and we were able to collect quite a lot of data. And today I'm presenting just the analysis of the analysis of the oxidation state of the uranium. And this is just to show you, so for the 3 soils, we managed to collect data for across the full profile of the depth profile. And we had, and also this picture I wanted to put them because you can see very clearly the change of color and after like about 15 centimeters depth. And when we look at the uranium and total iron concentrations in these depth profiles, we see that there is high concentration of iron up to these 15-20 centimeters, so this change of color as expected by the color. But then this is not following, the uranium is not following the same profile for all the soils, a bit in the soil 1 and soil 3, but not in the soil 2, which is very low, and then there's a peak at the deepest layers, and this is on the 3 of them. Unfortunately, we cannot see the soil 3, but there's an increase of uranium, but there is very low iron. So we have also SRD data. And from the linear combination fits of the spectroscopy data, we can see that there is oxidized uranium as expected on these soils, that it predominates most of the depth profile, but there starts to be an indication here after 28 centimeters depth, indication of a bit of uranium 4. So we have to do more analysis of this synchrotron data to try to understand how the uranium is bound in these soils. And in the sediments, we try to also get a depth profile results, and these they look a bit different. So sediment 1 is the closest that it was to the mixing zone, so it's very similar to the soil, and also we didn't get to go so deep. So there is only uranium 6 on this sediment. But on the sediment 2, which was actually in the north part of the pond, and was underwater, this is Millard collecting that core, and we have after 20 centimeters, so it was very low in uranium, the first 20 centimeters, but we managed to measure, and it was uranium 6. And then after 20 centimeters, there is this peak of uranium, which is not correlated to iron, and is actually uranium 4. And this point, this 2,000 milligrams per kilogram, it has is 100% is uranium 4. So we need to identify what's happening, or what type of uranium, how is if it's uraninite or if it's in another form of uranium 4. And just briefly mention it that Mila did the study of the bacteria and archaea at these different depths, and is gonna try to correlate the effect of microorganisms with the uranium redox chemistry. But then the last question we had, it was like, okay, but then this soil is retained, but what will happen? Is it immobile or not? And from these soils, and so we ran some flow-through column experiments with this soil from the mixing zone, from 2 different depths. And these were chosen because we have different concentrations of uranium and different concentrations of iron. So it's high iron and then lower iron. And these were leads for up to 14 days. And this we selected 3 types of water that represented different scenarios, which was if there is a more a freshwater input, there's about with pH 7. If there is another plume of acid rock drainage, so water with around pH 3, and then the third scenario was if there is a liming ongoing, if the water has a higher concentration of carbonate. And what we saw is here I'm only presenting the uranium in the effluent, so this is over time. We measure all of the elements too, and we saw that with the fresh water, there is an apparent, it's very low uranium release, and there is an apparent steady state release after 600 per volume, so about 10 days, and then it's about less than 1% of the initial uranium in the soil that is being released into the effluent. With the ARD water, it's another story. There is a much higher, enhancement of the uranium release, and it's two orders of magnitude higher, and it hasn't reached equilibrium. But actually, after this leaching period, there was about 75% of the uranium in the soil was already gone. And with the carbonate water, we have an enhanced release comparing to the fresh water, so it's much lower than I would expect, but it's higher than the fresh water. But interestingly, it's only with the soil, the deeper soil. The one is at 20 centimeters, not with the one that is higher, which is very similar to the fresh water. So, and also there was thorium in this water. So it's quite interesting. And so we need to do some more uranium solid phase speciation, because it seems that it has a key role in this uranium mobility in the soils from Tara Root. So I haven't finished with that data because we had been time in February, but from the signs of this from the reacted soils at pH 7 and 3, we have oxidized uranium, and still have to process the data for pH 2 reactive soils, and also the EXAFS to try to understand how this uranium is bound in these different layers of the soil. And just so conclude, this was a very quick summary. So a concluded remark is that this Tara Root site, it turned out to be a very interesting site for studying the environmental impact of acid forming alum shale. And since we also measure the alum shale, that is not just contains these NOR elements, but also a lot of like cadmium, arsenic, and so we have looked at all of this, and so the site can be considered as a multiple stressor site, and with has very complex mobility of contaminants. And so just the articles will come up this year, so just keep an eye on them. And future work is I got a master's student, so we are gonna run some column experiments with this sediment that contains reduced uranium, and see if there is any difference with soil, the upper layers. And last week we were collecting more samples, and we decided to, well, we cannot see it in this screen, but there is a further south pond, which is a connection, and it's so we were there, and it's full of water now. It wasn't 2 years ago, and we have, but the pH is about 6, and it's not completely close to but there is a deposit here. So we are gonna maybe take some samples and compare, because maybe there is a neutral rock drainage there. And so the investigation continues. And that's it. Thank you for your attention. I'll take any questions.
Thank you very much for your interesting presentation. So are there any questions in the audience or online? No, nothing online. One.
Good.
No.
So fine.
Everything's clear.
Yes, okay. Sorry for that. It doesn't look.
No.
This. Yes, Laureline. Yes.
Yes, a question.
Thank you, Estela. Yes, to try to make a link with the presentation we showed before, do you try, or do you have in mind to try to model the leaching experiments with a KD, for example, and so see if the KD fits with the experiment made by Michael or IRSM? And so.
Yeah, actually, I thought about doing the modeling for the. Yeah, once we identify how the uranium is bound and the solid phase speciation, I'll try to do a reactive transport model with, and I think we discussed it in the last work package meeting, that if I'll try to use the constants that they are being NKT, that they are producing within the Radon Norm project. Yes, it's on the plan if I find time. Yes, yeah. Hopefully within before the Radon Norm ends. Yes. Okay, thank you.